Alright, this is the lesson 1 video for unit 9, polynomials, and this is the intro to polynomials. So we'll start out with some definitions, learning some of the terms, and then we'll look at some of the basic features of a graph. This ties into investigation number 1. You didn't have to do investigation number 1, but it's a good way to introduce you to the unit. A monomial is a one-term expression. That's what the stems mean. Mono means one, nomial means term. So one-term expression, that's a number, a variable, or a product of number of variables. So for example, examples of monomials would be like 3, 8x squared, or just simply x. Each of those on their own, is a monomial. A polynomial is either a monomial or the product, or the sum of many monomials. That means they're put together. Sum means by addition or subtraction. The word polynomial breaks down to mean many terms. So what's an example of a polynomial? Well, it could be something like 4y cubed minus 6x squared plus 9y. Something like that. There's pluses and minuses. Each term is separated by a plus or a minus. Now, the standard form of a polynomial, we're going to work with everything in standard form. The standard form of a polynomial puts the terms in decreasing numerical order. That means the exponents go from highest to lowest. Finally, the degree of a polynomial is the highest or the largest exponent that it has. And we'll talk a little bit about that in just a second. We can name polynomials based on their degree. So here, I'm going to do the left side of the chart first, and we'll go back and do the right side. If I have a degree of 0, right, that's like 5. That's a constant. Now, the reason it has a degree of 0 is because this is technically like 5x to the 0 power. But any number raised to the 0 power is equal to 1. So it's really 5 times 1, which is just 5. So a number by itself is a constant. A polynomial of degree 1, the exponent on the x here is a 1. That would be called a linear function. Polynomial with degree of 2, exponent of 2, is called quadratic. We've worked with quadratic functions before. Degree 3, so the highest exponent being a 3, that's called cubic. Degree 4, highest exponent of 4, is called quartic. And the last one, degree 5, is called quintic, like quintuplets. Those are 6 words you should know. You should be able to classify a polynomial according to its degree. Now, some other words you might hear us say that you don't necessarily have to memorize, but it's good to know them, is classifying polynomials based on how many terms they have. Now, remember, a term is something separated by a plus or minus sign, right? So in this polynomial expression, we had 1, 2, 3 terms. So the number 5 by itself has 1 term, so that is called a monomial. Remember, 1 term, mono. This linear expression has 1, 2 terms. They're separated by a plus and minus sign, x and 4. So there's 2 terms. It's called a binomial. This quadratic, there's no plus or minus sign, so there's 1 term. This is also a monomial. Now the next one here has 1, 2, 3 terms. They're separated by plus and minus. So a 3-termed polynomial is called a trinomial. This quartic expression has 2 terms, so it is a binomial. And finally, this quintic expression has 1, 2, 3, 4 terms. It is called a, no fancy name, polynomial of 4 terms. Nothing fancy there. They ran out of fun names after 3. All right, you need to know the left side of this chart. Okay, you should be able to look at a polynomial and tell me its name based on its degree. All right, so let's put each of these polynomials into standard form, so exponents from highest to lowest. We'll decide what the degree is and then classify it using those terms on the left side of your table here based on its degree. So the first term in number 1 is 9x squared. That is the highest exponent, is the squared. The next term is plus a 3x because it's positive, and then plus 5. Now the degree here, the highest exponent, is a 2. So any polynomial with degree 2 is called quadratic. Now if you remember this from the year, go ahead and pause the video and see if you can classify and put these in standard form on your own, and then come back and check your work. Number 2 here, I start with the highest exponent, which is x to the 4th. It looks like I have 2 different terms with x squared. I have 10x squared and negative 6x squared. Those combine to be positive 4x squared. Then I get a plus 4x. And finally, on the end, minus 12. The degree of this polynomial, the highest exponent, is 4. So we call that a quartic. Quart means 4. That's the step. The next polynomial here, highest exponent is 3, so 3x cubed, minus x, and then plus 5 on the end. Degree here, the highest exponent is 3, so we call that a cubic polynomial. All right, last one. 2x to the 5th is the highest exponent, and then I have a minus 4x squared. The degree, the highest exponent here, is a 5, and we call polynomials of degree 5 quintic. Quint means 5. All right, hopefully you remember doing those, so we are good to move on to talk a little bit more about what the degree does for us. All right, degree tells us a lot of things about the polynomial. It tells us, firstly, about the end behavior of the graph. The degree also tells us the maximum number of turning points that a graph has. And finally, it tells us the total number of roots, which are the solutions. We also call those x-intercepts or zeros. Right now, the number of roots is not necessarily have to be real x-intercepts. All right, roots are going to be real and imaginary. So those are some terms that might have an I. All right, I is going to come back in this unit. Let's talk a little bit about end behavior. End behavior deals with the ends of the graph, or the arrows. All right, so when I'm looking here, I have the first polynomial, which is called y equals x squared. The degree of this polynomial, the highest exponent, is a 2, so we call that quadratic. Now it says A is the number, that's the leading coefficient, the number in front of the x squared. Here's 1. Well, that number 1 is positive. Right? It's a positive x squared, so that's why my graph is opening up. When I look at the arrows of my graph on the end, they're both pointing up. So when we do this formal end behavior notation, ask your teacher if you need a little help with this. I'm going to help you walk through trying to interpret it. This means as x goes to negative infinity. So as x axis goes to negative infinity, which is going to the left, the y values, your arrow, looks like it's going up, right? It's pointing towards the sky. That means it's going up towards positive infinity. Then as the x's go towards positive infinity, so as the x's go to the right to positive infinity, that's where positive infinity is, the y value, oops, put my highlighter back, the y value is going up, which means it's going towards positive infinity. Let me try to straighten that out a little bit there. That's a little bit better. All right, the next one. The degree here in this next polynomial is 4. That's the highest exponent. So it's called a quartic polynomial. The first term is a negative. That's why my arrows are both pointing down. Now let's talk about end behavior. As x's go to negative infinity, so as x goes to the left, that's where negative infinity goes. The y values, the arrow is going down, which means the y values are going down towards negative infinity. As the x values go to the right, towards positive infinity, the y values are still going down towards negative infinity. So for the first two, my degree was even, 2 and 4. And it looks like for even degrees polynomials, we investigated this in investigation 1, the arrows go in the same direction. So they're either both going up or they're both going down. You can tell if they're both going up by if the leading term is positive or if the leading term is negative. All right, now the degree of the next one. The highest exponent here is 3, so it's called cubic. The leading term is positive. So when you look at your graph here, you should see that it has a positive trend. If you connected the ends of the graph with a line, like I did, the graph is going up, has a positive trend. That's how you know that the leading term is positive. Now, let's talk about end behavior. As my x's go to negative infinity to the left, my arrow down here is going down towards negative infinity. As my x's go to the right, to positive infinity, the arrow's going up towards positive infinity. So this one with an odd degree, the arrows are going in opposite directions. At the next one, the degree of this graph is 3 again, it's cubic. The first term is negative, and if I connected the ends of the graph, if I connect the arrows, I would see that the trend is going down. It is negative. So when I do my end behavior, as x goes to negative infinity to the left, it looks like that arrow is going up to infinity. And then as x is going to the right towards positive infinity, the arrow is going down to negative infinity. All right, the end behavior takes a little bit of practice, so ask your teacher for some help. But hopefully, if you understand a little bit about how to read the notation, that the understanding will come. Now let's put this together. We've talked about it a little bit. If our degree is even, so even ones are going to be these two graphs right here. If the degree is even, 2 or 4, the arrows both go towards infinity or they both go towards negative infinity. That means they both go up or they both go down. If the leading term is positive, that means if there's not a negative in front, if there's a positive sign, the arrows are going to go up or towards infinity in the positive direction. If the leading term is negative, if there's a minus sign in front, the arrows go to negative infinity, which means they go down. That's the easiest one, right? So the arrows both go up or they both go down. Now, if the degree is odd, right, that's going to be these two over here on the right. If the degree is odd, that means one arrow is going to go towards infinity, one arrow is going to go up, and the other arrow goes towards negative infinity, or goes down. So let's see, if the leading coefficient is positive, like the third graph here, that has a positive trend. And we saw that by connecting the endpoints of my graph. So my graph's going to have a positive trend. If there's a negative in front, it has a negative trend, like graph number 4, and the arrows point down. So that's one thing that the degree tells us. It helps us figure out where do the arrows of my graph go. The degree also tells us a little bit about the number of turning points that a graph has. So if I have a polynomial of degree 1, that's a line. So I'm just going to sketch a line here. You can do the same. There's my line. It doesn't look like that turns at all. It looks like with degree 1, that graph has 0 turns. It's straight, it never changes direction. With degree 2, you can sketch a picture. I'm going to make one that looks like this. It looks like this graph of degree 2 has 1 turn on the bottom. So a quadratic function with degree 2 will turn 1 time. When I get to degree 3, there's actually 2 options here of drawing a degree 3 polynomial. The first one is going to look like this. So I'm going to come up, I'm going to flatten out a little bit, and then go back up. That's actually what your parent function for the cubic function looks like. I know it flattens out in the middle, but that's actually not a turn. The graph never stops going up. It doesn't go down and back up. So that first graph for degree 3 actually has 0 turns in it. Another way to draw a degree 3 graph would be to go down, turn, and then turn again. Remember, when we have degree 3, that's an odd degree, so the arrows are going in opposite directions. When I look at that graph, it looks like I have 1 turn, 2 turns. So that cubic polynomial has 2 turns. Finally, a degree 4, even degree, so the arrows are going to go in the same direction. There's 2 kind of ways to draw this graph. The first one is going to look kind of like the degree 2 graph, only it's going to be a little wider at the bottom. That degree 4 graph has 1 turn, but it's just really long. So degree 4 graphs could have 1 turn. They could also look like this. They could kind of look like a W. Now that graph has 1, 2, 3 turns. So that quartic graph has 3 turns. So as I look at this, it looks like the most times that a polynomial can change direction is equal to the degree minus 1. So in the last one, degree 4, 1 less than that is 3. That's the most times that you can turn on a quartic graph. For degree 3, 1 less than that is 2, and that was the most times you could change direction for a cubic graph. All right, last little bit of notes here. Let's talk about number of roots. Now remember, roots does mean x-intercepts, but it doesn't solely mean x-intercepts. Okay. Talks about total roots. Now in this particular example, we are going to look at the number of x-intercepts of the graph, but typically when we get later on in the unit, we'll notice that degree also tells us just about the total roots, all right, and solutions. So degree 1, there are 2 options. You can either have no x-intercepts, so that would be something like a horizontal line, or you could have 1 x-intercept. You could cross the x-axis 1 time. When I have degree 2, now, go back, degree 1, remember that is an odd degree, odd number of 1, so that's why the arrows are going in opposite directions. Degree 2, these are quadratic parabola functions. You can either, don't draw that. You can either cross 0 times, which means that you would draw your parabola and it would never actually cross the x-axis. It could have 0 x-intercepts. Your graph could have 1 x-intercept where you come down, touch the axis, and bounce back up. Or you could have 2 x-intercepts where you come up and through and cross the x-axis 2 times. When I have degree 3 polynomial, since my arrows are going in opposite direction, I actually have to cross the x-axis. There's no way, don't draw this, there's no way I can draw an arrow going in opposite direction that won't cross the x-axis, because eventually that arrow on the right will come up through because it's going to infinity. So I have to have at least 1 x-intercept here. So I have to have 1. So let's draw this graph. So as I cross the axis there, there's 1 x-intercept. I could have 2x-intercepts, where I come down, come back up and touch, and go back down through. It's going 2x-intercepts, or I could have 3x-intercepts, where my cubic graph goes through every time it turns. So degree 3, odd number, the arrows are going in opposite directions. Finally, degree 4, the arrows are going to go in the same direction because 4 is an even number. You could have 0x-intercepts. You could have a graph that looks kind of like this M, never crosses the axis. You could have 1x-intercept, where my graph comes down and touches the axis, bounces off, and then squiggles up above. So that would be an example of 1x-intercept. You could have 2x-intercepts, where so I'll make a similar kind of graph. I'm going to come down and cut through, and then wiggle above the axis. Now there's lots of ways to draw these graphs. These are just a couple examples. You could have 3x-intercepts, where you come down, up through, and then come and touch the axis. That would give you 3. And you could have 4x-intercepts, where you cut through every time and cross the axis 4 times. So it looks like the maximum number of x-intercepts or roots that you could have that are unique or different is actually equal to the degree of the polynomial. So here in degree 4, I had 4x-intercepts as the most. Degree 3 had 3x-intercepts as the most, and so on. Now let's go back to what the degree tells us. The degree tells us about the end behavior. It tells us if the arrows are going to go in the same direction or opposite directions. The degree tells us the maximum number of turns that a graph can have. So is it going to turn, it's always going to turn at most 1 less than the degree times. The degree also tells us the maximum number of roots that the graph has. It could have up to the degree's worth of real x-intercepts, but the total number of roots in general is always equal to the degree. All right, so even though for like this quartic function right here, there's 1 x-intercept, there's still actually 4 roots. Just some of them are imaginary because they don't all cross the x-axis. Whereas over on this graph, there are 4 roots and also 4 x-intercepts. They're all real. So some of our roots will be imaginary, but the number of x-intercepts can at most be the degree. All right, that's it for the notes here. Go ahead and try to practice. Make sure you know a little bit about how the degree works for polynomials, and then we'll move on to some other stuff.